So before giving the actual simplex algorithm, I want to revisit duality, but this time specifically for linear programs. So in the primal domain, we want to minimize C transpose X subject to the inequality constraints. And here we have n variables that live in an m-dimensional space. And we have m inequality constraints. Wrong. So if I want A to be m times n, then we have n variables. So I can say X is element of Rn, and we have a total of m inequality constraints, yes. And then in the dual, we have a maximum. We looked at, or we derived the dual through these Lagrange multipliers 3 hours ago. And we noted that this was the dual for this specific primal problem. And this time I have m variables and n equality constraints. And then a few simple inequality constraints. Now, what you call primal and what you call dual is really arbitrary. So rather than maximize minus B transpose Z, I could just as well write, I want to minimize B transpose C subject to the same. And they are really the same. What matters is that here you have your matrix A and there you have your matrix A transpose. Now, weak duality can be shown. We showed it using the Lagrangian and dual functions, etc. But it can also be shown in a simpler way for linear programs. So if X is primal feasible, and Z is dual feasible, then we can say that C transpose from these equality constraints up here is the same as minus Z transpose A. Sorry, C and Z. So I can write C transpose X as, using this identity here, as minus Z transpose A times X. But we also have these inequality constraints. So A times X should be less than or equal to B. And that's why here we have a negative sign. This should be more than or equal to minus Z transpose B. So you see on the left-hand side, we find that the value of the primal problem is always larger than or equal to the value of our dual problem. And strong duality is afforded by exploiting the complementary slackness condition. So I can measure the duality gap. I'm taking the value here of the primal problem minus the value of the dual problem. And I'm inserting the formula just seen above here. So it's minus Z transpose AX plus Z transpose B. And I can multiply out the Z. So this gives me B minus AX. And if I now look at this as that being the Lagrange multiplier that is associated with these inequality constraints, then I can say that by complementary slackness, this should be 0 at the optimum. So for this to hold, I should put a star on all the x's and all the z's. So the duality gap is 0. Strong duality holds. And as before, I can say that if Zi star is larger than 0, then necessarily the second term must be 0. So AI transpose X star must be BI. So the ith inequality is tight or is active at the optimum solution, and vice versa. If AI transpose X star is smaller than BI, then I know that that Lagrange multiplier is 0. Okay, now to the actual simplex algorithm. Invented by Danzig in 1947. So we proceed in 2 phases. We first find an extreme point to start with, and if you're in a very high dimensional space, how do you want to find an extreme point of this polyhedron? Actually, you can do it using the simplex, but this is sort of a recursive scheme. So for starters, we will assume that we already are at an extreme point, and we will then develop the simplex algorithm, and later we will see a trick how that same algorithm can be used to find an extreme feasible point in the first place. So we're, like Münchhausen, bootstrapping ourselves here. And secondly, so we've started at some extreme point, let's say, and let's say minus the cost vector is pointing in this direction. So the optimum solution would be here, at this vertex. What we do is that we move from one vertex to the adjacent vertex and so on until we're at the optimum. And again, in high dimensions, this polyhedron is going to be a multi-faceted body, and it's not totally obvious how to move from one neighbor to the next and so on. And this is just what we're going to look at now. So secondly, we move from this to an adjacent vertex such that we lower the cost. Until we have reached an optimum. And to simplify the exposition, we're going to make a couple of assumptions that do not change anything about the intuition of the algorithm, but it means we don't have to deal with corner cases. So we assume that the problem is given in the inequality form. You've seen this often now, but I'm using the matrix A in the next row, so I'm writing it down again. I'm assuming that the rank of A is n. So this implies the polyhedron has at least one extreme point. I assume the extreme points are non-degenerate. By that I mean, let's say in the above example, this would be a non-degenerate case. That would be a degenerate one. So multiple inequalities that define the same subspace. And as said, I assume that we already are at a feasible extreme point. I can omit the feasible. So when I say extreme point, it's already clear that it's a vertex of the polygon. Okay, so we are going to do this in two phases. First, we will look at how to find an adjacent vertex, and then how to actually find an adjacent vertex of lower energy or lower cost. So we're at an extreme point and have a set I of active constraints. These are the rows of my matrix A where the inequalities are actually met, so they're equalities. And we also define a matrix A sub I which holds only the active constraints. So these funny indices are those indices that are part of the active set. Now for an extreme point, if we are in n-dimensional space, if we want to specify a single point in n-dimensional space, we need n equations. And we assume that our system is non-degenerate and so on. So I can say that the rank of AI should be n. So this is for all extreme points. And if we now look at two adjacent vertices, they have all but one constraint in common. That's the definition of being adjacent. So I should perhaps look for an image. It's not what I wanted. Bernhard, what is a... can you not see my screen? Okay, I was looking for rhomboids and I didn't get what I wanted. Okay, yeah, now you can show everybody. So here are a couple of examples of, those are just sketches of what polyhedra could look like. And this is an extreme point, and let's say those extreme points, they have all but two constraints in common, but this extreme point and that extreme point, they have all but one constraint in common. Okay, so in this particular case, we have a 3D space, so three constraints or three planes meet in a single point. And if we compare those 2 points, they're both defined by those 2 planes, but the third plane differs. So adjacent vertices have exactly n-1 common constraints. And we can now find all adjacent vertices at the same time by solving a system of equations. So to find all adjacent vertices, we solve the following. We say AI times delta x. This is my direction which I want to move from my current coordinate x. Should be minus ek. And ek is a unit vector that has a 1 in the kth position. Yeah. Yeah, well, k can be larger than, or, k will be at least as large as n. So why? I did not say anything about k here at all. You know, I could just, this should be a capital K, but I could also just have written n here. Okay, so all I want, well, I think we're talking about the following. We have A, which I said was of dimension m by n, and I require that in order to identify a point, I want the subset that is active to have rank n. So, and there's no problem in achieving that when m is larger than n. So if we look at our 2D example here, so in this case here, m would be 5 and n would be 2. And if I have degeneracy, then there can be another, so here for example, k, capital K could be equal to 3, but the rank would still be 2. So well, it's just, I want to, so extreme point should be a single point. And if I'm in an n-dimensional space, I need n independent equations. And as soon as 2 of my equations are linearly dependent, then I no longer specify a point but a line. And then my rank is not n but n minus 1. Okay, so let me write this here more explicitly. So I have 0 except for the kth component, which would be minus 1. Now the inner product being 0 means that delta x should be orthogonal to all rows of AI except for the kth row. And let me sketch or try and sketch this. I'll try and do a 3D sketch this time. So I am having a total of 4 planes here. There is one plane pointing in this direction. Let me call this A1 transpose. Then I have one plane here pointing towards me. Let's say this is A2 transpose. Then I have a plane here pointing away from me. And finally A4. Again, these are all normal vectors on their respective planes. So A4 would be orthogonal to this plane, and so on. And let's say we start here. This would be x. And I now want to find a neighbor. And I'm taking out, or I'm putting a minus 1, let's say, in the first position. That means I'm looking for a vector delta x which is orthogonal to A2 and is orthogonal to A3. This is what the zeros say. And then I want a minus 1. I want my new vector to point away or to project onto the negative part of my original vector A1. So I could put all these vectors, I could now try and put them all in this point here. This is my point x. And well, now it becomes hard, you know, to draw this thing in 3D, but essentially being orthogonal means I need to stay in this plane here, I need to stay in the front plane, I also need to stay in the back plane, and I want to move away from this one here. So overall, this gives me a delta x in this direction here. Is the intuition clear? Okay. So I had to solve the system of equations, and I get out a delta x, and now I check if this new direction is a feasible half-line, because it could be, you see, imagine that there is no constraint A4 here, then I could simply move along this edge up to infinity. So if A, this is now my full constraint matrix, A times delta x is less than or equal to 0, then I can move in this direction without bounds. So alpha would be some non-negative multiplier. So if I do not have any normal vector that has a positive inner product with my new direction, then I can simply keep on walking in this new direction without ever hitting a new constraint plane. That would be a feasible half-line. If it's not a feasible half-line, then I want to know how far I have to walk until I meet the next constraint. So in this case, I need to find the proper value for my multiplier. So I will say my adjacent vertex is going to be x hat. It's going to be the old x plus alpha times my new direction, delta x. And I need to find the proper value for the multiplier. And I'm now going to look for the closest constraint. So I'm looking for, amongst all constraints, that limit my, which I'm going to hit eventually. Among all of those, I'm going to look for the one which is closest. Subject to some normalization here. So x was my old point. So this is the old coordinate here, x. And this is, the numerator tells me how far my old point is away from the new putative constraint I, because when the numerator goes to 0, then I would have reached that constraint. And then now I need to normalize, because I did not say anywhere that these normal vectors here should have unit lengths or anything along those lines. So I need to normalize, both by the length of these unit vectors and by the angle which my new direction will form with these unit vectors. Okay, so at this point we have found an adjacent extreme point, but we do not yet know if it has lower or higher cost. And evaluating this cost is what we will do in the next step. As as a comment, we started with something that had full rank, and our new active set should also have full rank, and we can verify this property. So I said that AI has full rank. So we were able to solve for delta x. And the updated AI again has rank n for the following reason. Because in the direction that we moved, the new direction was orthogonal to all the old constraints, except for the ones we were taking out of the active set. So this was holding for all I in the old active set except the one which we have taken out. So this is for all I in the new active set. And in addition, we have included a new constraint j. And if you look at the minimization here, we were minimizing only over new so we have a new constraint aj transpose delta x. And because we were only minimizing over terms that were larger than 0 here, we know that this is 0, whereas larger than 0, whereas those were 0. And from that, we can conclude that aj is linearly independent of all the ai in the previous active set. So of ai, where I was the old active set, except for the constraint k, which we took out. So to make long story short, we had full rank, and we moved in a direction that also guaranteed us to keep the full rank. That's the important part. Okay, so we found, yes, question? So what is this thing here? Sorry, this is a AI, where I are all the indices in the old active set except k that we've taken out. So we have a recipe to find extreme points or adjacent extreme points, but now we want adjacent extreme points with lower cost. So to do that, we also need to be able to find out if we already are at an optimum. So we want to find an adjacent vertex of lower cost. And before we embark on a journey, so before moving in a new direction delta x, we should verify if we are already at the optimum. And now we can use the equality constraints of the dual problem. So in the dual problem, we had that A transpose Z should be minus C. So if you go a few slides back, this is what we were using where we were discussing the duality. We had this formula here that C equals minus A times Z. Okay, so this is what I'm again using here, and there is a graphical interpretation for that. Namely, we want to see if the active constraints have the negative cost vector in their normal cone. So this is A1 transpose, A2 transpose, A3 transpose, and I'm now looking at this corner here. Let's say my cost vector minus C is pointing in this direction, and I can now copy my vector A1. Sorry, this is starting to be messy. A1 transpose. So A1 transpose is orthogonal on this constraint, and then I have A2 transpose, which is orthogonal on that constraint. And if my negative cost vector lies in the cone spanned by these two, so this is the cone that they span, if my negative cost vector lies within this cone, then I know that I'm done. Whereas if you looked at let's look at this vertex here. This is the cost vector minus C, and the normal vectors are this one and that one. Again, here's my cone, but now the negative cost vector is outside the cone. So I know that this is an optimum and that is not an optimum. And this is what I'm going to use now. So I'm using not the entire equation now, but just the active set. And I'm asking if this equation holds for non-negative multiples of all of these vectors. So here you see these two vectors, they span a basis as two-dimensional space, so I could express minus C as a linear combination of these two. However, I would have to take a little bit of here constraint 2 minus something minus a little bit of A3. So that's not a convex combination. Or the multipliers would not be all positive, whereas here they are all positive. And well, to find out if this is true, we can solve this system of equations. So we solve for Zi and find out. Well, then there are two cases. If indeed all values of, or all components of Zi are non-negative, then we are done. We are at an extremum. Otherwise, we have to do some more work. Namely, otherwise, we select one of the directions. So we select some k which was not yet in order. So we select some k with zk less than 0. So we're picking a constraint that was lying on the wrong side of our coefficient vector. So let's look at this example here. I can take multiples of, let's say this is gamma times A2 transpose. True. Okay, I was trying to reconstruct the cost vector minus C as a combination of those two here. So this was A3 transpose, and that one was A2 transpose. And I could take a positive multiple of A2 minus a multiple of A3. So A3 would have a negative value if I solved this equation here at that extremum. So this is why I want to get rid of this equation number 3. But sometimes there are, if you work in a higher dimensional space, there may be several bad directions from which, or several bad constraints from which you want to walk away, and then you have to pick one of them. And there is some arbitrariness here in which one you select. Okay, now we're interested in what is going to be the cost. So we can determine, so we select some k with zk smaller than 0. Then we determine delta x as before. Which was by solving a linear system of equation, by saying A defined on the active set only times delta x should be minus ek, where ek is the direction that we want to move away from. And then we can compute the new cost. So new cost is going to be C transpose of x plus our positive multiplier times the direction that we want to move in. So I can multiply this out and say this is C transpose x plus alpha C transpose delta x, and C I can now substitute with this equation that or this expression that we had previously used. Namely, I write it as Zi transpose AI. So that together would be minus C. And delta x itself was given by a to the minus 1 minus a to the minus 1 times ek. So I can insert this here and write C transpose x minus alpha Ci transpose ai. And now I'm substituting here for delta x by saying plus ai to the minus 1 times ek. And this cancels. And this picks out the kth component. So I have C transpose x plus alpha times zk in the end. Okay, and alpha is a non-negative multiplier because, so we determined alpha here, and the numerator is non-negative and the denominator is positive, so alpha overall is non-negative. And zk itself was less than, no, was strictly less than 0, because that's how we selected it. So it's strictly less than 0. and hence this is going to be less than z transpose x. So this is the new cost, this is the old cost, and we find that overall the cost decreases if we move in such a direction as if we move away from one of the unhelpful constraints. Okay, and there we are, just in time. We can summarize this in an algorithm. Do you need more time? Yeah? Well, if I exclude degenerate configurations, then I will always move some non-zero distance to the adjacent vertex. If you admit degenerate cases, then you can get stuck in a point. So you are right. I should say cost decreases for non-degenerate cases, and I had assumed from the beginning on that here we're just dealing with non-degenerate in order not to run into this problem of getting stuck in one vertex and cycling. Okay, so now all of these findings can be summarized in the Simplex algorithm. Again, at the outset, I assume we are at an extreme point x with an active set I. We proceed in 3 steps. First, I want to try and express my negative cost vector in terms of the normal vectors of my active constraints. So this was the thing where I wanted to make sure that my negative cost vector lies in the normal cone of my local inequalities that are locally active. And to do that, I need to solve this system of equations. So we're solving linear system of equations, which is one of the expensive steps in this entire algorithm. And if it so happens that all of my z are non-negative, then we can terminate. We are done. Otherwise, however, we need to continue. We choose some, where again there is some arbitrariness in which one, and there are different heuristic recipes to suggest which one you should pick. So we pick one of the negative components, one of the active constraints which is not in the way between our current extreme point and the direction in which it would like to move. And we solve the other system of equations which will tell us the direction in which we want to walk. And again, we have to solve a system of linear equations, so again, this is going to be expensive. And if A times delta x is less than or equal to 0, we have a feasible half-line. And because after the result of step 1 we're moving into a profitable direction, we would again be done with an optimum value that would be minus infinity. Otherwise, we need to do some more work, namely to move exactly to the next vertex. We want to go from one extreme to the next, so we should not stop too early, and we certainly should not stop too late, because then we would go infeasible. So we update the active set. My new active set is going to be the old one without the constraint k that we took out, which is replaced by a new constraint j that we take in. Where j is the first constraint that we hit when we go in this direction. So here, for example, let's say this is my old point, and this is delta x, and I must stop at the first constraint, not at the second or third or so. So this is what this argmin is doing. So this is the first constraint that I'm going to hit, and we find a new extremum, which is the old one, plus alpha times this direction, where alpha is going to be this thing here. So bj minus aj transpose x and normalized. So there's our simplex algorithm, which assumed that we start at an extreme point. This is the final problem that we need to solve. How do we make sure that we start at an extreme point? And here comes the trick. So finding the initial extreme point to start with. We can we start by putting the LP that we really want to solve in the following form. And that works in general because we've seen that an unbounded x can be rewritten as x plus minus x minus, and then put bounds on those and so on. So we can always put it, any LP in this form. And now secondly, we create an artificial LP and solve that. Namely, we minimize t subject to ax less than or equal 1 minus t times b. So here we have a new LP. And now we can start at a feasible point, namely x equals 0 and t equals 1 is a feasible point for this auxiliary problem. So if we insert x equals 0 and t equals 1, we find that 0 is less than or equal to 0. So it's not the optimum, but it's going to be a feasible point. And now we can use the algorithm that you've just seen to find the optimum feasible point. And we have two possible outcomes. Namely, we could find an optimum value of t star that is greater than 0, which means we're never going to recover our original problem. So the original problem in that case is not feasible, and we're done. Because obviously if you set up contradicting constraints, then there will be no solution to your linear program, and you get no solution. If, on the other hand, your optimum solution is going to be 0, then the x star, which you find at the same time, is an extreme point of your original LP. Well, of this one here, of the LP in number 1. And then you can start using the simplex on that.